All right, we're going to review for exam 7 on chapter 9. And I'm working from version 2. I think that's the one I gave you, wasn't it? Version 2. Yeah, version 2. Good. We're working from the same, singing from the same hymnal. All right. And I've got several highlighted. So let's take a look at this one. Which of the following molecules contains a central atom with sp2 hybridization? All right, so we've got several molecules to choose from. sp2 hybridization, which implies what? It needs 3 groups, right? Okay, so 3 groups means trigonal plane. So what we've got here are Lewis dot structures, and what we're looking for is a central atom that only has 3 groups around it. Now they could be bonded atoms, or they could be lone pairs. Could be a combination, right? So if we look at A, what does A have in it? Well, it has aluminum with 4 groups, phosphorus with 4 groups. That's a central atom. Chlorine wouldn't be considered a central atom because it has no other bonds to it. All right, so these are both sp3s. Oops. Go there, goes here. All right. So that one won't work. How about B? Let's see, boron. It has fluorine. That looks like a good candidate to me. All right, 3 groups and no lone pairs. All right, B looks good. If we just check the others to be safe, C has the central atom phosphorus has 3 bonding pairs and 1 lone pair, so that makes it sp3 hybridization. And the same thing for the hydrazine. Both nitrogens have 4 groups around them. Beryllium dichloride only has 2 groups around. So it's actually octet deficient. And it would only be sp hybridized. So we found the right one. B should be it. All right. Moving on. Number 3. Consider the molecule in the following hybridization choices. What is the hybridization of the carbon atom that is double bonded to oxygen? All right, we got 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. And we've got a triple bonded nitrogen here. And we've got hydrogens there. And we've got, that's the one they're looking at. And then we have a chlorine here and a hydrogen. Okay, so if we're focused on the double bonded to oxygen, this carbon right here, right, we have 3 groups and they're no lone pairs. And we know that because there's an octet around this carbon, 2, 4, 6, 8. Can't be any lone pairs around carbon because carbon is second period. It has no access to d orbitals. Right, so it's not going to exceed the octet ever. Okay. So that means with 3 groups, it's sp2 hybridized. Okay. It needs 3 hybrid orbitals. Right. About 5. So we got this molecule. Oh, we want to know the hybridization on every carbon. And those numbers are just sequential, like from left to right, carbon 1, 2, 3, 4, and 5. So we got 5 carbons. 1, 2, 3, 4, 5. And let's see, we've got a double, single, single, single. double, single, single, single. Then we got this nitrogen out here. And we got this two hydrogens here. And we've got a double bonded oxygen there. We've got a hydrogen here. And we've got two hydrogens here. This is 1, 2, 3, 4, and 5. So all we need is to find out what are the groups around each carbon. Well, this hydrogen, these two hydrogens are 1 and 2 groups, and then the third one. So that's sp2. We only have three groups around that carbon. 1, 2, 3. This one has 1, 2, 3. It's also sp2. Okay. This one has 1, 2, 3, and it's also sp2. This one has 4. These two hydrogens are bound to that carbon. So that's 2 plus these two is 4, which is sp3. And this one has 2, 4, 6, 8. That octet only has 2 groups. It's sp hybridized. So it's 2, 2, 2, 3, and 1, which would be A. Okay. And it's moving on. 6. So we want to know the hybridization of selenium with selenium hexafluoride. Okay, selenium is in the sulfur oxygen group, so it has 6 electrons. 6 times 7 is 42. So we have 48 electrons. Selenium, and then we have 6. 1, 2, 3, 4, 5, 6. 2, 4, 6, 8, 10, 12. So that's 36 electrons left. 2, 4, 6. If we put 6 more electrons around each fluorine to make the octet, 6 times 6 is 36. So we used them all up. There we go. Okay, so that means selenium has what? 6 groups around it. 6 groups is octahedral, and we need 6 hybrid orbitals. And so sp3 gives us 4. We need 2 more. We get those from D's. So D2sp3 would be the hybridization for selenium. All right. How about number 9? Okay, a pi bond is the result of. Okay, so if we have 2 atoms here, and we bond them together, what's the first bond? The first bond is always a sigma. And then the possibility is for a pi bond and maybe another pi bond maximum. Okay, so how does the pi bond form? Well, the pi bond forms from unused, unhybridized p orbitals. If we only have one of them, then we just have that one. If we have another one, then there'll be right angles, unused p's to overlap for the second one. But for one bond, the overlap of not s orbitals, not s and p orbitals, not 2 p orbitals along their axis, because on the axis is always a sigma. So D, let's see, what does it say? Sidewise overlap of 2 parallel p orbitals. That's it. Yeah. So D would be the answer to this one. That's how you get a pi bond. Okay. Number 10. Use the molecules below to answer the next 3 questions. All right. Well, in this case, We only had 2 questions. There must have been a third one somewhere. Okay, so we have Roman numeral 1, 2, and 3, and they all have a hexagonal carbon backbone. In organic chemistry, when we draw lines like that, every place that a line intersects is a carbon. Okay. So this first one has a double there, a double there, and a double there. Second one has a double here and a double there. And the third one only has a double there. Okay. Now the formula says C6H6, which means that in organic chemistry, we don't write the carbons and we don't write the hydrogens either. So each one of these has a hydrogen on it, like that. That means for C6H8 is the next one, C6H8. That means we'd have one carbon there, one hydrogen there, hydrogen, hydrogen, hydrogen. And here you have 2 hydrogens. So I give you the 2 extra ones. And then for this one, we have C6H10 probably. Yeah. So for this one, we have one there, one there. We have 2 here, 2 here, 2 here, 2 there. And each one of these is a hydrogen. Okay. All right. Now, what's the question? Which molecules have p orbitals that share an electron pair to create a pi bond? They all do. They all have p orbitals that overlap sideways to make pi orbitals, pi bonds. That's a pi, 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 pi. So all 3 of them are creating pi bonds. Only this one has 3 of them. This one has 2. This one has 1. This one's special though. This one has a special delocalization of electrons that form that in our lecture slides. You saw the donuts, the 2 donuts on either side of this benzene molecule. This is especially stable, and this one is aromatic. Aromatic implies several things, but one thing for sure is it implies extra stability. This molecule is much, much more stable than this one or that. Now you could get some delocalization here around those bonds like that. That one won't do anything. But this one is extremely stable, which means if you're going to break this up into its elemental parts, then it'll take a whole lot more energy into this one than it will to that one or that one. Just a side note. Okay, how about the next one? Number 11. Which molecules have equivalent carbon-carbon bonds throughout the molecule? All right. These are single bonds, right? So they're single sigma bonds. They have a certain bond strength, and a bond length is going to be like, just for argument's sake, this long. These double bonds are going to be stronger because you've got a sigma and a pi, and the bonds are going to be shorter. So this is a shortened bond. These are roughly the same length. These are roughly the same length. These 2 here, these 3 bonds are probably the same length because you get that delocalization. And these 3 are different. But all of these are exactly the same length, the same strength, and they're all in the same plane. That's characteristic of aromatics. So the question was equivalent carbon-carbon bonds. This one right here, Roman numeral 1, which would be A for our answer. These are more unstable because they have these differing bonds. This is extremely stable. When a tree falls and starts to rot, it has these large molecules. It has cellulose. Cellulose is made from glucose. Lots of them linked together. Thousands of them linked together. And they're linked together in such a way that we can't digest them. You need microorganisms to digest them. And that's why termites go in there, because they have microbes in their gut that can digest the cellulose. But the cellulose goes first because it's easy to break those bonds. The next thing that goes is the side branches off of the other molecules. There's another molecule in there called lignin. And lignin has lots of these benzene structures in it. They're extremely stable. So when the fungus and the termites and those guys go in there and chew on it, the lignin is only digestible by specialized enzymes. And they go after the side chains first, chop those off, and you're left with these benzene rings. It takes a very special type of enzyme that's characteristic of only a few organisms that can break that lignin. So it's the very last thing to go because it's the more stable. Number 12. The electron configuration of a particular diatomic species is, all right, we didn't go over this in detail in class because we just didn't have time. But remember when we formed these molecular orbital, the molecular orbitals from our atomic orbitals. This is a sigma that's derived from a 2s atomic orbital. And then that means we also have an antibonding, bonding and antibonding drawn from that 2s. Then we have a sigma from the 2p's. Okay, and then we have a pi from the 2p's in this example. And then we have a pi star. So there's no mixing here. Remember, the sigma pi bonding first, and then the pi star, and then the sigma star will come next. But in this example, we don't use that because we don't have enough electrons. So we'll erase that. But this particular example is there's no SP mixing. All right, so we're told that this one is full with 2 electrons, right? Sigma, that's just one sigma, right? So it's like that. And then this sigma has 2. We fill from lowest to highest. This one should only have 2. Now, this one can have 4 because there are 2 pi's possible. Right, so that one has 4. How many are in this one? 2. That means with these 2 in that antibonding, we have 2 electrons. And they have to go in like that according to Hund's rule. Right? You can't pair them up until you got 1 in each one of the degenerate orbitals. So now what are they looking for? What's the bond order? Okay, bond order is bonding 2, 4, 8 minus 2, 4 divided by 2, and that would be 2. Bond order would be 2. Okay, that's why the answer is D. Now, just while we're here, would this particular molecule be paramagnetic or diamagnetic? Paramagnetic is the one that is attracted into a magnetic field. And you have to have unpaired electrons to do that. This is paramagnetic. If we stopped right here, right, didn't have that, then these would all be paired. And it would be diamagnetic. It would be like dinitrogen. It would just flow right through the magnet field. I think we've got one like that coming up. I thought I'd make that point while we were here. Let's see. Well, 13. All right. As the bond order of a bond increases, the bond energy does what? We increase the bond order, we increase the bond energy. So we increase the first one. Increase bond energy. And the second one is bond length. As you increase the strength of the bond, you draw the atoms closer together. So the bond length is decreased. Okay, so increase, decrease would be C. $15. All right. How many unpaired electrons in the F2 2 plus ion? So we have F2 2 plus. Before we put up the ionic structure, molecular orbital structure for this one, how many electrons do we have to deal with here? Let's see. Just looking at the electronic structure, we're starting with a 2s. So if we put the total number of electrons in here, that would be 18 minus 2 to make the 2 plus would be 16. But we're leaving out the 1s's, right? The 1s would have 2 electrons. So we're going to take off 2 more electrons, so 14 electrons. 14 valence electrons are the ones we're dealing with that particular structure. If we're starting with 2s, right, that means we left off 1s and 1s star. Right? We just chop those out. Okay. All right. So now we have this one. And let's see. It looks like we have sp mixing on this one. No, we don't. Sorry. No, we don't. We have this one, 2p. We have this one. And then we have anti-bonding. And then this anti-bonding. Okay. So if we've got 14 electrons to go in here, wait a minute. Maybe we only have 12. I think we only have 12, right? Because this would be 2, 4. Sorry. This would be 4. And this would be 12. 12 electrons to deal with. So this holds 2, 2, 2. This holds 4. This holds, let's see, 2, 4, 6, 10, and then 2 more here. So we don't even use this last one. Okay. The order of molecular orbitals are this. How many unpaired electrons? Okay, so this one we have 2 degenerate orbitals for the pi, which means 1 here, 1 here. So we have 2 unpaired electrons. Okay. Did I lose you at this point? I subtracted only 2, but with this lower level, we got 2 here and 2 here. And so 2, 4, 6, 8, 10, 14, 16. That would be the total here. And if we chop those 4 out, then 2, 4, 6, 10, 12. That would be this one. I had to get the right number of electrons. All right. Moving on. Number 19. Let's see, the hybridization of the central atom in ClF2 plus. ClF2 plus. Now I assume from that formula that the central atom is chlorine. And we have 7, 14 minus 1 to make that positive. So that's 20, right? 20 electrons. So chlorine, we have fluorine here and fluorine here. That's minus 4, which is 16. 2, 6, 8, 10, 12. Minus 12, this is 4. So 2, 4. Jennifer's here. Okay. Let's see. I don't see Desiree. Okay, so the hybridization around this one, got 1, 2, 3, 4 groups. sp3. We need 4 hybrid orbitals to accommodate 2 bonding and 2 non-bonding pairs. That would be C. All right, 21. Which of the following does not contain at least one pi bond? Okay. A, B, C, D, and E. All right, what's our first one? H2CO. H2CO. I believe that is formic acid. Carbon dioxide. C2H4, C2H4, ethylene, C2H6, ethane, and none of the above. None of the above what? At least one pi bond. One pi, at least one pi. Okay. Let's do ones that we know really quick. Carbon dioxide, we've done that one so many times. Right. There you go. It's got two pi bonds. Right? So it's does not contain at least one. This one contains at least one, so it's not our answer. How about this one? Well, let's see. We have 2 electrons there, 4 there, and 6 there. Right? Well, that's 12 electrons. We have carbon in the middle, oxygen, and 2 hydrogens. 2, 4, 6. Right, so we have 6 electrons left over. 2, 4, 6. I've used them all up. Now we make a octet for carbon. You just take those 2 and make a double bond. Right. So that one's got a pi bond in it. Anytime you have a double bond, you got 1 pi. Triple bonds give you 2 pi's. How about this one? Let's see. I think we've done this one before, actually. 2 times 4 is 8, plus 4 is 12 electrons. We have a carbon, 4 hydrogens. 2, 4, 6, 8, 10. So we have 2 electrons that have to go somewhere. Now we make an octet, make a double bond out of those. Right? That's got a pi bond in it. How about this one? Let's see. This is 8 again. 2 times 4 is 8. And this is 6, so we've got 14 electrons now. So we have carbon, 1, 2, 3, 4, 5, 6, right? 6 hydrogens. 2, 4, 6, 8, 10, 12, 14. That's it. That has no pi bonds in it. They're all sigmas. Right, so this is the one right here that answers that question. '24. Complete the Lewis structure for the following molecule. So we're given a backbone here. That was nice of them. All right. I'm going to draw it. That's the way we would draw it in organic chemistry. I'm going to draw it in such a way that we can tell who's who and who goes where. So this CH3 looks like that. And then it's bound to this carbon, which has that hydrogen off to the side like this, plus another methyl group up here. Okay. Then we have another carbon bound to it, and it has an oxygen. Let's put the oxygen. Yeah, we can put it here. And then we have a carbon, and then the nitrogen. Okay. So if we're going to do the Lewis structure, and we now have the backbone, we need to count up the carbons. 1, 2, 3, 4, 5 carbons. So 5 times 4 is 20 electrons, valence electrons. 1 oxygen is 6. And 1 nitrogen is 5. I'm counting valence electrons here. And then hydrogens have 1 each. 1, 2, 3, 4, 7. Right. 1, 2, 7. I think that's all. Yes. Just 7. So 12, 18, 38. Correct? Yeah, 38 electrons. Okay. So far we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We've used 26 electrons. So that's 12 that we have to find a place for. We can't start from the outside and work your way in. We can't do anything with hydrogens. They're already used up. So we can use this oxygen and this nitrogen to use up the other 12. 2, 4, 6, 8, 10, 12. So we used up all our electrons. Now we have to make an octet. Right? That one's got one, that one's got one, that one's got one. This one doesn't have one. So we'll do like that. That makes an octet there and keeps an octet for oxygen. This one has 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8. So there's your Lewis structure. Now let's count the sigma and the pi bonds. The sigma bonds are all the single bonds. That's we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 sigmas, and then look for doubles and triples. There's 1 pi, there's 2 pi's, so we have 3 pi's. Now, if we want to check ourselves, that means we need 16 bonds total. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the answer should be 13, 3, which would be D. Excuse me, E. E would be 13 sigmas and 3 pi's. Okay. Let's see, 26. I got my stopping point marked in here, so we're not going to run over. We got the skeletal structure. N, C, C, N. Draw the Lewis structure and answer the following. How many pi bonds does this molecule have? All right. What we have to assume is this skeletal structure has no other atoms in it. That's it. That's the total. C2N2 would be the molecular formula. Okay. So there's 5, 10, and 8 be 18. Right? 18 electrons. Right? 2, 4, 6, 8, 10, 12. So we have 6 more left over. 2, 4, 6. Right? Let's see if I did that right. That'd be 10. That'd be 8 total. 10, 2, 4, 6. Oops. Let's try that again. I think I made a boo-boo. Let's start over. Do over. So we have 18. 5 and 5 is 10, and 4 and 4 is 8, 18. So that's the total. Then we got 2, 4, 6. Minus 6. Here we go. Well, maybe I was right. 2, 4, 6, 8, 10, 12. Nothing on the carbons yet. There we go. I like that a whole lot better. Okay, now that we've used up our electrons, we got to make an octet. So how do we make an octet? Well, carbons don't have any electrons, so we can't move it to the inside here. These 2 carbons are single bond together. But we can make an octet by doing this and doing this. Like that. Right? How many pi bonds does the molecule contain? 1, 2, 3, 4. That's 4 pi's. Oops. Yeah, 4 pi bonds. Right? That was now 27. Which of the following molecules contains the shortest carbon-carbon bond? We're looking for the shortest carbon-carbon. Now that could be one sigma, it could be a sigma and a pi, or a pi, two pi's and a sigma. So the shortest carbon-carbon bond would be the one with, if we have access to it, in other words, the bond strength, shortest bond length. So the shortest bond is going to be, let's see, this bond is going to be longer than this bond, which is longer than this bond, right? Because the longer bond is the weaker one. That's weaker. This is stronger still. So it's going to get shorter and shorter. So the shortest one is going to be the one with, well, let's see. If we have C2H2, C2H4, C2H6, and C2Cl, Cl2, Cl4, excuse me. Right, we've drawn these before, right? This one is a single bond carbon with 3 hydrogens around each carbon. That makes an octet. This one is our ethylene, like that, with our hydrogens. This was acetylene with a hydrogen on either side. This one is like that one with 4 chlorines. Right? Since we're looking for the shortest bond, we're going to go for this one. It's the strongest carbon-carbon bond. If we had not been given this one, then we would have to break a tie between this one and this one, because they're both double bonds. So, I mean, that's not part of the question, but let's see. The answer to this one as given is A. That's acetylene. But if we had to break a tie between these two, how would you do it? Well, you would look at it this way. Is there anything in either one of these molecules that would weaken the bond? I mean, if we don't have these hydrogens and chlorines to look at, they look like the same bond, double bond. But chlorine is more electronegative than hydrogen. It is going to draw away electrons from that shared sigma and pi bond. It's going to weaken the bond and cause it to pull apart. So this one would be weaker than that one. But that's not required to answer the question, of course. I just threw that in for free. 28. Okay. When comparing diberyllium and dihydrogen, okay, we got 4 possibilities here. Be2 is more stable because it contains both bonding and antibonding. Okay, looking at the answers, we need to know the molecular orbital structure of those 2 molecules. Yeah. So let's see. Dihydrogen versus diberyllium. Right, we looked at dihydrogen earlier, not actually in the lecture part of the course. And it's only got 1 s orbital, so it can form a 1 s bonding and a 1 s antibonding. And there's 1 electron for each, which means 2 goes here, right? So it doesn't even use that. Okay. This one, beryllium, has 4 electrons each. So it has 8 electrons. And it's working in the second. So it's going to have 1 s, excuse me. it's going to have a sigma molecular orbital made from the 1s and a sigma star made from the 1s. Then it's going to go to sigma made from the 2s and sigma star made from the 2s. And with 8 electrons, it has 2, 4, 6, 8. So actually, Be2 should not exist. Right? What's its bond order? 4 minus 4 divided by 2 is 0. All right, so they're giving us that one theoretically. We know this one exists. That one probably doesn't exist. All right, let's look at the possible answers. Be2 is more stable because it contains both bonding and anti-bonding. No, that makes it less stable. In fact, that makes it improbable. Roman numeral 2, H2 has a higher bond order than Be2. Yeah, 2 is true. Has a higher bond order. This is a bond order of 1, and this is a bond order of 0. 3, let's see. H2 is more stable because it only contains sigma 1s. Well, yeah, that's why it's a bond order 1. So 3 is also true. How about 4? H2 is more stable because it is diamagnetic, whereas no. If this existed, it would be diamagnetic also, because there are no unpaired electrons, right? You've only got one molecular orbital on each one of these, and they're all full. If they existed, right? But they don't. Now, let's go down. Now, I'm curious. Let's go down and look at that. Excuse me. I'll get there. Down. Here it is. Well, that's boron, that's carbon, that's not, they don't even have beryllium in here. There's beryllium. All right, so beryllium should be, let's see, beryllium should be 2s. Yeah, that's the right order. Yeah. Okay. Let's go back up to 28. There we go. All right. So theoretically, 2 and 3 are true. But if it were up to me, I'd say Be2 can't exist anyway. Now, if we made an ion out of it, like which one? If we subtracted, if we made it a positive ion, what if we did this? Where would the electron come from? It come from here, right? That means the bond order would be 1/2. If we made a 2+ ion out of it, then it would be bond order 1. Now that could exist, right? Because it has bond order of 1, which would be a single bond. But that's not what they said. They said Be2. That's it. Neutral Be2, which does not exist. We don't predict that it would exist. Right? Let me put it that way. It's just my luck that some graduate student was successful in making one of those. 29. And if his PhD thesis depended on it, and it could be done, he probably would do it. He or she. 29. Which of the following species is paramagnetic? All right. A, B, C, D, and E, right? Oh, this is none of these. We're looking for paramagnetic. Paramagnetic. That means all paired electrons. So we have C2, O2F2, O2F2, and Li2. All right. Which ones are going to have mixing? All right, here's the dividing line between nitrogen and oxygen. Non-mixing, mixing. So this is going to be SP mixing. Yes. No. No. And Li2, yes. So these are going to be non-mixing, these are going to be mixing. All right, let's do the non-mixing first. Let's lay out their molecular orbital series. All right, sigma, we're just going to use the we're just going to use the valence orbitals. 2s, sigma star, 2s. Then we have pi, excuse me. No, sigma 2p, pi 2p, pi star 2p, and sigma star 2p. So this one will have the same situation. Okay. 2p, 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 star, 2s, and 2s. Then the ones with mixing are going to be the same for this part of the series. Then we're going to have this sigma 2p. Then we're going to have a, let's see. I think this one swaps, doesn't it? No, this one swaps. Is that right? Let's check to be sure. That's why I put this in here. It's as much for me as it is for you. Okay. So oxygen is okay. Carbon. Okay, carbon is going to be star. Yeah, the pi and the sigma bonds are switched. So in this one, we'll have pi here, 2p, sigma, excuse me, 2p. Then we'll have pi star, 2p, and then we'll have sigma star, 2p. And down here, the same thing. Sigma 2s, sigma star, 2s, 2s, and then we'll have pi 2p, sigma 2p, pi star 2p. And we may not need all these. But I figure I put them in here first. That way we get this part of the problem worked out. And now all we have to do is count up how many electrons have to go into those orbitals. All right, so carbon, we're going to use valence electrons because we're starting with the 2s. So the 1s goes out. So the carbon is going to have 8 electrons. Oxygen is going to have 12. Fluorine is going to have 14. I'm counting just valence electrons. Lithium, actually lithium is only going to have 2 valence electrons. All right, so let's fill them in. All right, 2, 4, and 4 is 8. That's it. That's all for carbon. All right. Oxygen, 12. 2, 4, 6, and 4 is 10, and then 2 more here, right? There we go. And then fluorine, difluorine. We have 14. 2, 4, 6, 4 is 10, and 4 is 14. Correct? 8, 6, yeah. And then 2 here. That's it. Okay, now we can answer the question. All right, better go back to 29, huh? Here we go. Which of the following species is paramagnetic? We need unpaired electrons. Right? So carbon, these are paired, these are all paired, these are all paired. How about these? Paired, paired, we got 4 here, right? Those are all paired, right? So it's not this one. And it's not this one. How about these two? 4, we have here, here, like that, like that. Oh, that's a good candidate. That's paramagnetic. How about this one? Oh, we got 2 orbitals here and it's full. So it won't be that. So O2 is the only paramagnetic in that group. All right. Now, I did it the hard way. But what you can do during a test, since you're going to have that, you're going to have this thing down here at the bottom. Keep going. Right here. Right. The only one that'll throw you maybe is the lithium. But you know the lithium is only going to have this one right here. So you just put both electrons in it, you're done. Right? They're paired. But the rest of them, fluorine, oxygen, and carbon. Let's see, fluorine, yeah, fluorine, oxygen, carbon, they're in the group. So you can see at a glance, the only one with unpaired is oxygen. So let's go back to 29. Oops, more. There we go. And look at 30. Let's see. For how many of the following does the bond order decrease if you add 1 electron? Okay, we got carbon and fluorine already. So let's keep those for 30. And there's carbon. And let's see. And what are other choices? Carbon, boron, and phosphorus. So B2 and phosphorus 2. Well, all right. How many does boron have? Well, it has 3 valence electrons. Right? It's going to be mixing. So do we have mixing here? No, that's not mixing. Okay, we need mixing. So this needs to be a pi. This needs to be a sigma. With 3 times 2 is 6. 6 electrons. 2, 4, 6. There we go. That's diboron. Right? And phosphorus. So phosphorus is going to have 10 valence electrons, but they go into and there's going to be mixing. So this is 3s and sigma star 3s. And then we're going to have pi 3p and sigma 3p. Let's see, is that going to give us enough? 2, 4, 4 is 8, 10. Yeah, that'll give us enough. So we'll have 2 here, 2 here, 4 here, 2 there. This one's already done, that one's done, that one's done. Okay, so we've got all of our molecular orbitals set up. And go back to the question. How many of the bond order decrease if you add 1 electron? Okay, so we're going to add 1 electron to this thing. We're going to have a like that. Where does the electron go? Oop, that was full. So we've got to go to, got to add our sigma back in here. 1 electron there. How about this one? We add an electron. That electron's going to go here. Right? This electron, that's full. So we got to go to, let's see, sigma star from a 2p. Now we're going to add electron there. And phosphorus should be mixing, right? So it's going to have 2, 4, 6, 10. We're going to make that 11. So this is going to be 11, 15, 7, and 9 electrons. 2, 4, 8, 9. That's good. Okay, what goes beyond this? If we go that, then we're going to have this one. Correct? That's next. All right, we add an electron to that. Okay, which one is going to decrease bond order? The one that decreases bond order by adding an electron is if we add an electron to an anti-bonding orbital. We add an electron to a bonding orbital. That's not going to decrease it. We add an electron to a bonding orbital. That's an increase, increase, decrease, decrease. So difluorine and diphosphorus are going to decrease their bond orders because we add an electron to an anti-bonding orbital. So for how many of the following does the bond order decrease? 2. 2 of them. This one and this one. Okay. And then here's the last one I had marked. This is halfway. Right. So if we want to do the other half on Tuesday, then we'll do this one and stop. Yeah, that'll be a good place. Okay. 32. All right. Order the following from shortest to longest bond. Don't forget the effect of atomic radius and orbital size. Okay. So let's look at C2, B2, H2, and N2. C2, B2, N2, H2. All right. Bond order. All right, we have to draw it again. Carbon is going to be sigma 2s, sigma star 2s, and this is sp mixing. So the next one will be pi 2p and sigma 2p, and then if we keep going, it'll be pi star 2p. We may need it, we may not. So valence is 8 electrons, 2, 4, and 4 is 8. So that's it. That's all we need there. Okay, diboron. It's going to be mixing also, but it has what? 3, 6 electrons. So we have this one, and that's 2, 4. I guess we need this one also. 2p, which has 2, 2, and 2. And dinitrogen, that's also mixing. 2 times 7 is, no, 2 times 5 is 10. Yeah, 2 times 5 is 10. So we have mixing here. S with a pi, 2p, sigma, 2p. Then we have pi star, 2p, and maybe sigma star 2p. Yeah. We have 2, 4, 4 more is 8, and then 2 here. So that's all we need. And then dihydrogen. That's just 1s with 2. Okay. Order from shortest to longest bond. So which one's the strongest? Well, let's do the bond orders. Bond order. So we'll have 6 minus 2 divided by 2. All right, so that's 4. That's 2. Bond order of 2. This one has 4 minus 2 divided by 2 equals 1. All right, 2 plus 2 is 4 minus 2. This one has 4, 5, 6, 7, 8 minus 2 divided by 2 equals 3. And hydrogen, we've done that before, that equals 1. Okay, so that gives us the bond order. But notice these these are using second period orbitals. They're bigger. And this one only using first order, first 1s orbitals. So these protons are going to be closer together because the orbitals are smaller. Right? So this one is going to be the shortest one. Dihydrogen will be the shortest bond. Right? And then from shortest to longest. Then since these are all made from the same cake mix, we can order these by the next shortest would be the strongest N2. And then we would go to C2 and then to B2. So that would be from shortest to longest bond, which would be A. Okay? The trick in that one is to see this effect right here. Okay, that's it. And when we come back on Tuesday, we'll pick it up with 34 and finish that review. Part 2 review on Tuesday, and then we'll have an exam on Thursday. Then the following week is the last week of classes. And that's the week we'll use both Tuesday and Thursday to review for the final.